Peering deep into the universe, astronomers probe the clash of cosmic forces. The obliteration of matter and energy. We glimpse the limits of time and space in the strange death of a star. There is no vision more reassuring. The endless cycles of the sun and the moon. The heavens ceaselessly turning. The night sky appears eternal and unchanging. Modern astronomy has given us a much different vision of a universe that roils and vents its rage. That vision comes together in the death throes of a giant star. Its surface is a stormy sea of fire. As superheated gas rises and sinks. Giant waves form. Solar tsunamis 1,000 kilometers high. Immense loops of hot, electrified gas, larger than the Earth, blast into its atmosphere. Deep within its core, the star has begun to collapse in on itself. That causes the star to erupt in a violent supernova. In its wake, the explosion leaves a trail of colorful filaments and luminous, billowing clouds. Remarkably, the death of one star gives rise to a whole new generation of others. This cycle of death and birth has defined the history of our Milky Way galaxy and that of billions of other galaxies in the universe beyond. Our own vision of space has been shaped by a handful of rare exploding stars bright enough to be seen by the naked eye. In the year 1054, stargazers in North America spotted a supernova near a crescent moon. The same event was recorded in China, Korea, and the Middle East. The astronomer Tycho Brahe saw one in 1572. He wrote, "I was led into such perplexity by the unbelievability of the thing that I began to doubt the faith of my own eyes." Johannes Kepler recorded the next one in 1604. Galileo used it to make his case for a whole new approach to astronomy, based on the idea that change is a fundamental part of the cosmos. To find out how stars shape our universe, astronomers are employing an arsenal of new technology. From giant telescopes perched on high mountains to a fleet of instruments in space. When we look through a telescope at the stars, we are seeing the visible light they emit. But this is just a small part of what is known as the electromagnetic spectrum. At one end of this spectrum are short, high-energy X-rays and gamma rays. At the other end, long, low-energy radio waves. Huge arrays of radio telescopes are now being used to collect low-energy radio signals emitted by stars far off in the universe. Scientists use them to look through nebulas and gas clouds, to see the objects inside. At the other end of the spectrum are ultraviolet, X-rays, and gamma rays. The short wavelength of X-rays allow doctors to send them through our bodies to look for bone fractures. Astronomers look for them in space as evidence of the most violent processes in our universe. What shapes the cosmos at large is visible close to home. Our Sun is a medium-sized star with a surface temperature of nearly 6,000 degrees Celsius. Deep within its core, the temperature rises to 15 million degrees Celsius. High heat and pressure initiate nuclear fusion reactions that convert hydrogen to helium, releasing energy. The Sun, like all other stars, spends its life fighting gravity. Energy pushing out from its core keeps its outer layers from collapsing in. The Sun produces enough energy to hold gravity in check for billions of years. Not so for a large star. It burns hot and fast, steadily packing its core with heavier and heavier elements. When its core reaches a critical threshold, it no longer produces enough energy to counter gravity. It collapses, then explodes. Destruction is by no means a supernova's only legacy. The explosion seeds its environment with carbon, oxygen, iron, and other elements necessary for life as we know it. Shock waves from the blast can trigger the birth of new stars. In fact, star hatcheries set in motion by supernovae percolate all around our galaxy. Among them is a great luminous cloud of gas and dust known as the Orion Nebula. Here, astronomers have pinpointed solar systems in the making. When clouds like these become dense enough, nuclear fusion begins. Stars and solar systems are born. Another fate altogether awaits the exploding star at the center of this cosmic drama. In the wake of the blast, its highly compressed core remains intact. Imagine planet Earth compressed down to a tennis ball. That's a neutron star. Some can spin at incredible speeds, hundreds of times per second. When a so-called pulsar was first detected by radio telescopes, its signal was thought to have come from a faraway alien civilization. The Crab Nebula is the shell of the same supernova that caught the attention of so many cultures in the year 1054. Scientists have zeroed in on a pulsar deep within. They documented waves of radiation that have etched circular patterns in the surrounding gas. Some dying stars meet a fate that is stranger still. Nature, it seems, has contrived a monster. The scientist Albert Einstein once speculated about a star with such intense gravity that nothing, not even light, could escape its grasp. He dismissed this prospect as impossible. What once seemed beyond reason now defines the frontiers of science. Astronomers believe that when a star explodes, enough matter can collapse into its core that it literally exits the known universe. Gravity wins the final battle. From our vantage on Earth, we define our universe by familiar criteria, including the forms of light we find along the electromagnetic spectrum. But black holes defy discovery. How can we detect an object that emits no light? Astronomers spotted the answer in a flash of gamma radiation in the direction of the center of our galaxy. Radio telescopes zeroed in on the source and found jets of matter racing out in two directions. This is what they saw. A black hole that is drawing a stream of gas from a star's outer layers. As it flows in, it forms a spinning disk. The disk generates magnetic fields that twist around and channel some of the inflowing matter out into a pair of high-energy beams, or jets. Astronomers now know that black holes can pack so much energy into these jets that they accelerate to within a tiny fraction of the speed of light. It turns out that this black hole, known to us as GRO J1655-40, is streaking across space at a speed of 400,000 kilometers per hour, 4 times faster than other stars around it. Most likely, it was blasted like a cannon by the supernova that produced it. Black holes, with their ability to marshal extreme energies, are more than just curiosities in our universe. There is a breed of large black holes that dates back to the earliest times, when the first generation of stars were being born at a rapid pace. When these primordial giants died, some gave birth to black holes. Gravity force-fed these black holes a diet of stars and gas as matter collapsed into the first galaxies, and as small galaxies merged into larger ones. A few of these primordial monsters grew to billions of times the mass of our sun. By launching powerful jets, they heated up the regions surrounding their host galaxies. That put a stop to the flow of gas into the central galaxy, stunting its growth and allowing smaller galaxies on the periphery to form and grow. But the impact of these black holes did not stop there. This image from the Chandra X-ray Observatory shows a cluster of galaxies called Hydra A. It's enveloped in immense hot cavities glowing in X-ray light. There is a jet visible in radio waves blasting out of its central galaxy. Gas along the edge of the jet was found to contain high levels of iron and other metals, probably generated by supernova explosions. By pushing these metals into regions beyond, the black hole seeded more distant galaxies with the elements needed to form stars and solar systems like ours. Supermassive black holes can be seen in nearly every large galaxy in our universe. We've caught a growing number in the act of powering massive jets. We are beneficiaries of the violent life cycles of stars. And yet, we are separated from them by scales of distance and time beyond anything we experience on Earth. That separation is thrown into sharp relief by the flight of the twin Voyager spacecraft launched in 1977. After exploring the outer planets and their moons, these crafts are now plying the outer limits of the solar system. Tens of billions of miles from Earth. Traveling at 16 kilometers per second, Voyager 2 will pass within 4 light-years of the nearby star Sirius. 290,000 years from now. From our tiny corner of the galaxy, we've discovered that stars not only light up the universe, they also seed it with the stuff of life. By witnessing the explosive end of a star, we gain fleeting glimpses into the power that shapes the universe and transforms worlds like our own. Since ancient times, we have asked, what lies over the horizon and beyond the oceans? Where does the world end? As we've pushed farther and farther out, our journey has revealed a solar system, a galaxy, a universe on larger and larger scales. And now, a new set of theories is telling us that time and space are incomprehensibly large. What will we learn on our search for the edge of the universe. If you could step away from our world, what would you see? How do deserts fit in with oceans? Or mountains with floodplains? What structures connect Earth to the other planets? The stars and beyond. The ancient Greek philosopher Aristotle believed Earth lay at the center of a series of 55 celestial spheres, with each moving in a way that predicted the positions of the planets or the stars within them. He saw these outer realms as home to the gods. They are made, he said, of a pure substance not found on Earth. The Greeks were also the first to see celestial events as natural phenomena, subject to human investigation. One skywatcher named Anaxagoras suggested that meteors are made of materials found on Earth and might have actually come from the Earth. He and other Greek astronomers helped build the foundations of science. But they would be shocked to see the discoveries being made by their counterparts today. The stars and planets that once harbored the gods are now seen as infinitesimal parts of a vast scaffolding of matter and energy that extends far out into space. Aristotle's model of a cosmos centered on the Earth lasted until the 16th century. Nicholas Copernicus proposed that Earth and the other planets instead revolve around the Sun. Based on his findings that planets have their own orbits, scientists constructed new models that described their movements over time. Copernicus noted, too, that the firmament, the stars, lay far, far beyond the solar system. Our model of the universe began to get much larger in the year 1609. When the scientist Galileo Galilei used the first astronomical telescope, he observed that the Milky Way, a broad band of light that rises up in summer skies, is actually composed of stars. Centuries later, astronomers discovered that the Milky Way is actually a vast revolving disk. They characterized the universe as an island of stars and gas, immense, yet still limited in size. This model of an island universe would soon collapse under the weight of scientific evidence. Working with the huge new 100-inch telescope on California's Mount Wilson, astronomer Edwin Hubble and an assistant named Milt Humison analyzed the light of fuzzy patches of sky known then as nebulae. They found that these patches were actually galaxies unto themselves, but located far beyond our own. They also found that many of these galaxies are moving away from us. The farther away they are, the faster they are receding. This discovery sparked the rise of a whole new model of the universe, one filled with countless galaxies that's growing larger all the time. Because it takes the light of these distant galaxies millions, even billions of years to reach us. The deeper into space astronomers peered, the farther back in time they ventured. To study the history of the cosmos, scientists opened larger and larger telescopes to capture light from ever more distant reaches of the universe. They began to see that the stars and the universe at large are not as peaceful or static as we had once believed. In an age of atomic weapons and nuclear physics, a whole new model of the universe emerged. A dynamic realm shaped by giant exploding stars, shock waves, and black holes. In this view, the universe had its origins in a violent primordial event. A Big Bang. The Big Bang model rested on four main pillars. That the universe as a whole is expanding in all directions. If you turned the clock back, you'd see that all matter and energy had a common starting point in space and time. The existence of light elements like hydrogen, which would have formed in very early times and later converted to heavier elements. That there is light wafting through the universe that was emitted when the universe was young and has stretched out over time into microwaves. Finally, it established a time frame for the evolution of stars, galaxies, and the large-scale structures of the universe. But this new model of a Big Bang universe proved incomplete. Recent precision measurements gathered by the Hubble Space Telescope and other instruments have brought a consensus that the universe dates back 13.7 billion years. Taking cosmic expansion into account, galaxies at the edge of the visible universe are actually 46 billion light-years away from us in each direction. What's beyond those galaxies? They have their own horizons that extend that much farther out. What's beyond that? Where does it all end? And how did the universe grow to such an immense size? Another observation puzzled astronomers. No matter what part of the sky you examine, the spread of galaxies, the density of matter, and the temperature are the same on large scales. To achieve this degree of homogeneity over its entire breadth, the universe would have to have expanded far faster and to a greater extent than allowed by the standard Big Bang model. How did the universe get so big and so uniform? A new cosmic model with a fresh explanation was waiting in the wings. It sprung from one of the most important scientific observations of our time, linking the universe we see around us to its earliest moments. The Space Shuttle Discovery lifted the groundbreaking Hubble Space Telescope into orbit on April 24, 1990. Another, more modest launch took place 5 months earlier. The Cosmic Observation Background Explorer, COBE for short, was sent up to capture the microwave light that was emitted when the universe was in its infancy. This light, the mission found, contained a pattern of hot and cold spots. The WMAP and Planck satellites have updated this observation by recording greater detail. In these images, scientists found the seeds of all we see around us today. Smooth on a large scale, but with variations on smaller scales. Astronomers set out to discover how the universe would have evolved from this cosmic template. In an age of computer-controlled telescopes and automated observing, astronomers launched international collaborations with the goal of mapping a large fraction of the visible universe in 3 dimensions. The cosmic map that has emerged leads us out beyond our own remote corner of the Milky Way. We move through our cosmic neighborhood, a collection of 20-odd galaxies known as the local group. Beyond that, some 50 million light-years away, we approach the densely packed Virgo supercluster, the nearest intergalactic city. Beyond Virgo, galaxies line up in vast walls and arcs. Here's how this pattern plays out on extremely large scales. the universe is a spider's web of galaxy filaments bounded by immense empty voids. To explain the origin of these immense structures, scientists proposed a more expansive model of cosmic origins. It's based on the discovery that energy is constantly welling up from the vacuum of space in the form of particles of opposing charge, matter and antimatter. The new idea, called inflation, holds that the universe sprung from these diffuse energy fields. They somehow tipped into a higher energy state, causing space and time to literally inflate. Tiny fluctuations in the primordial energy generated pressure waves, or ripples. As the universe evolved, these ripples gave rise to variations in the density of matter, which gravity then began to amplify. To link these ripples to the patterns of galaxies we see around us, astronomers have been using supercomputers to simulate the evolution of the universe going back to its early days. Starting in a time when the universe was 10% its current age, the simulations show matter steadily falling into denser and denser regions, where stars, galaxies, then galaxy clusters formed. Simulations like this are designed to replicate just a portion of the visible universe. The universe as a whole is now thought to be much, much larger. The fury of cosmic inflation would have caused the universe to go from atomic size to cosmological size within an infinitesimally short time. In the billions of years since its birth, the theory says, the universe as a whole would have grown to some 10 billion trillion times the size of the observable universe. That's a 10 followed by 24 zeros. Put another way, the whole universe is to the observable universe as the observable universe is to an atom. As incomprehensibly large as the universe is in the inflationary model, perhaps that's not even the limit. Four centuries ago, Galileo showed that our sun is just one of many stars. 8 decades ago, the astronomer Edwin Hubble showed that the Milky Way is one galaxy in an ocean filled with island universes. Newer observations have revealed the immense size of our galaxy. Then, clusters of galaxies. And beyond them, vast walls and filaments of matter. By drawing on an underlying physical process to explain the birth of the universe, the idea of cosmic inflation has led scientists to think in far broader terms than ever before. There are versions of the theory, for example, that suggest we live in one of many universes that may even coexist side by side. Like bubbles, these universes are continually rising up and expanding across the oceans of infinity. This idea amounts to a quantum leap in our sense of scale. By extending our ideas of the structure of time and space far, far beyond our visible horizon. Does it push us on our tiny, out-of-the-way planet into a smaller and smaller corner of creation? Or does our ability to assemble models that describe the larger universe somehow elevate our importance in the grand scheme of things?